Thank you for inviting me. You used the word bioreceptive design. It is true that I'm going to talk about it, but actually the title of the talk is about biointegrated design as a bigger umbrella theme for the research that we are carrying out. Not only at the biotA lab, but also at the C Bioma, with the C Bioma group at the IAC in Barcelona. Now, for me, what is really interesting and important is to look at how growth systems can be really integrated in our architectural fabric. And it's easy to say it and extremely difficult to do. Now, this is not a sort of random exercise. The idea is really to find new solutions. And I'm deeply convinced that there are two grand moments that are influencing us, which is obviously the deep, profound revolution in computational tools that we are using and the means in which we are operating, but also the biotechnology revolution that is ongoing, mainly in labs, and how that is having a direct or indirect influence. Now, I'm talking to those who are all believing in that, so this is nothing new. It's just the means in which we are approaching that probably differ slightly from group to group. So cellularity, tissue growth, time-based systems are all of great importance, extremely difficult to manipulate and control, especially when there's a big scale jump. And one of the biggest challenges that I have encountered so far, and I'm sure this is shared by many of those in the audience and the speakers, is the problem that what we do in the laboratory not necessarily applies straight away on a larger scale and vice versa. Now, the computational tools are really allowing us to simulate and monitor, but also predict and propose different types of geometrical systems, growth systems, emergent systems, which is obviously all extremely interesting. I'm not sure, I'm looking at the screen that doesn't move. Are you seeing a white image, or is that, this is interesting. I'm on page number 6, and the title is still on the screen, so I don't know what's happening with the slideshow. Is this happening? This is interesting. So I could start from the scratch again. Oh, wow. Can we? Now it's happening. Okay. So if I just scan through, so you see here some of these growth systems in nature, some of the cellularity that I was talking about. Again, I'm looking at actually this here. And some of the computational tools that are starting to simulate and predict through mathematical, but also through complex geometric equations, how to predict, how to control and monitor these biological systems. So lots of branching, lots of emergence in the way that these time-based systems are growing are part of the study. Now, one of the things that obviously is happening is that the area in which we are doing all this is, in the practices we are having, are changing from much more the design studio into the laboratory and back again. That's really interesting. This is Shneel Malik, who actually from the biotA lab has one of her pieces in the exhibition, creating robotically printed systems which mixes in a way innovative fabrication systems with biochemical engineering lab protocols. Again, to bridge the knowledge and to sort of create a new species of designer who is working with a knowledge that is cross-disciplinary is not an easy task. Now, in the biotA lab, we are very keen on cryptogams. This is shared with some of my colleagues, Richard Beckett and others, and that is that there is a world of very small species that are of great interest. Cryptogams are mainly algae, lichens, bryophytes, or mosses, also ferns, and they have been to a large extent neglected because they are very small, and the politics of greening cities has focused to a large extent on what is greatly visible, parks and trees. cryptogams are really interesting because they account for 7% of the carbon fixation in the air, and also 50% of the nitrogen fixation from the air. And this is a very, very large quantity. This was also only recently actually investigated by the Max Planck Institute in Germany, who found out that the role of cryptogams in the world is really very profound and is affecting our environment altogether. Now, there has been a very key shift in my understanding, conceptually, after doing 8 years of a PhD focused on skins, architectural skins, which is to realize that skins as membranes are really interesting, probably the most used metaphor in architectural terms. There's no building without a fancy skin. But barks are actually more interesting. And that is, barks are skins that are hosts for a whole ecology that grows on them. Tree barks are also geometrically very complex. It's a lot to do with water retention. It's to do with the ecology that grows and occupies and biocolonizes these surfaces. It's to do with orientation and environment. It's to do with the material, etc. But something that comes with it, which is odd, which we often don't like, what grows is unpredictable. And what grows has patchy patterns. Now, patchy patterns are difficult for architects who learned how to control geometry. And out of the history of aesthetics of cleanliness and hygiene that we had for nearly now 2 centuries, the patchy random occurrence on a surface is problematic. We have called it the aesthetics of impurity, which means there's something going on that usually is considered as displeasant or unpleasant or uncomfortable or even ugly. But there's something very, very interesting about the adaptation and the intelligence embedded in it. As you can see here, the patterns can change and adjust to the climate and occupy the surfaces that we have designed. Now, what is fascinating is that biocolonization happens everywhere. There's no material that is not biocolonized at some point in time in the exterior environment. But we had a period where we liked this, which was Romanticism. Romanticism actually delved into the beauty of impure aesthetics and this sort of nostalgia that the cycle between nature and what we designed was actually something fascinating. And I believe there's something to learn from that. There's something to learn from how we accepted in the period that this patchy, unpredictable growth was actually taking over surfaces and creating a dialogue with what we were designing in a positive way rather than a disturbance. Maybe a little bit lower. Can the sound be lowered a bit, please? This is a film that just shows how lichens are profoundly capable to absorb water. So what these species do is that they're capable of getting dry. Even a bit lower, please, the sound. So they're called poikilohydric. Can you make the sound lower, please? So the poikilohydric condition of algae and lichens and the cryptogams in general is that they don't have really a defense system for hydration. So they desiccate very easily, but that's part of their intelligence because they are switched on almost immediately if they get some level of hydration again. So the desiccation is almost immediate, but they become dormant. So the switching on and off is a very interesting phenomenon for these species because it makes them pretty much spread everywhere and resist the moments of lack of water. This image that you just saw here, or this small film, was actually taken in the mines of Rio Tinto. And this is another fascinating topic for me, which is in extreme environments, you have the adjustment of species a long time to very, very extreme conditions that we otherwise would not be able to thrive on. This in the Rio Tinto mines is to do with algae that adjusted to these highly acidic water conditions, but managed to sort of thrive in them. and it's worth exploring such conditions in more detail. So the environmental context is one of the most difficult for us to define when we pretty much survey, as architects, a space. One of the things we ought to do is to survey what grows in that space, and in much more rigorous manner understand really how the climatic, environmental conditions affect what might be or not growing in those conditions. And this is a very old piece of work that a student of mine, Steve Pike, did at the time at the Bartlett. This goes back now 17 years, where he put these different monitor vessels in different spaces of London and realized that the sterility of environment that we very often believed in is a complete fiction. In fact, every single program and occupancy of a space has a bacteriological setup that, if monitored and used on a bioreceptive surface, will create different patterns and different growth species to develop. So a biointegrated system is a very difficult one to achieve, but really interesting, because there's something about the transition between what is purely growing and what we are creating as a scaffold on which growth happens. Because as designers, we not necessarily are aiming all the time to redesign the species. We might, but we might be looking at what the hosts are, what's the scaffold, what's the substratum, which is very much the architectural condition on which the growth is happening and with which the growth is happening. So Marian and I designed this piece for the FRAC, and we called it at the time something else, but we realized it was the bioreceptive condition that we then later on started defining and studying in more detail in the biotA lab. So these wall components talk about this issue of the transition between what is designed as an inhibiting area and an area of growth enhancement. Again, really fascinating to define that not everything has to grow when we design it, that certain areas will actually be dry for a long period, but they will become receptacles for example, like in these cases, in these small components we designed in the biotA lab with some students, areas of concrete where algae will proliferate, and other areas where moss will proliferate according to the different conditions, sun radiation, etc. And here different patterns. And I declare my challenge here, which is that, again, it's easy to talk about it, extremely difficult to find the balance of design between what is growing and what is actually designed and in which this growth is happening. So again, a 3D printed transition between a scaffold that was printed with a cellulose material and a mycelium growth point in which the mycelium was growing almost into its negative geometry, which was created through these cellulose prints. At the IAC in Barcelona, with the Bioma group, we have looked at a lot of what I call paramateriality conditions. Means that there's a parallel or beyond the traditional material condition that we are looking for, and that is that materials nowadays, as we well know, can be composed of literally anything. And for growth purposes, this is of great significance because the pH level, the porosity conditions, the surface roughness can be manipulated and designed by us. And that will promote different types of growth on the surface or within the material. So this was with a student work where we introduced mycelium into the 3D printed cellulose matrix. And on certain areas, the mycelium was starting to take over the exterior, but in other areas it was just living within the cavity wall to strengthen and bind these different components together. Here you can see it a bit in section. So there's a sort of structural dimension to the mycelium growth within a controlled mechanism. With another one, again, a different material speculation and test, with another student at the IAC, we looked at using cactus mucilage, which was actually used in traditional housing in Mexico to promote a much more plastic, malleable, flexible, absorbent material that is partly plaster, partly concrete, and partly this cactus mucilage. And the design patterns have to do with studies of environmental change that happens. And another case where the bacteria that was colonized onto the surface was happening on one side, which is what you see on the image on, I guess, the right-hand side, and the left-hand side, which is the opposite side of the panel, where the water was running down through its runoff and absorbed into the ceramics. So what this means is that by a very careful control with the Kumela factory and ceramics in Barcelona, Nina Jutanovic was able to absorb water from one side and bring it in through this capillary reaction to the other side, where the bacteria was changing its coloration according to the amount of moisture that was present in the ceramics. Fascinating was that Tony Kumela was many years ago involved in creating the tiles for the Santa Catarina market of Enrique Miralles when he was alive. And we then found out that that was actually part of the scheme they wanted to create, which is tiles that could change color according to the environment. And here we were sort of almost 20 years later, in fact, realizing some of that ambition. So in terms of material studies in these compositions, as I mentioned, porosity, capillary action is of the essence. This goes into a very large and also very small scale, so the variance of scale is of key importance. We 3D printed, for instance, the sandstone, magnesium phosphate, concrete pieces where the bricks have a level of porosity not only of the material, again, to absorb water and retain water, but allowing these small pores to have growth. We are still studying these ones. These ones are exposed to the surrounding. And then I heard very often and thought very often about growing materials. And we are doing, obviously, slow progress on that, and something is happening. But then you get cases like this one here, where we went with our students to Sintra in Portugal, where you have these phenomenal romantic gardens. And by walking around one of the big wells in one of the gardens, you realize that the material is indeed changing through the deposition of calcium carbonate that is actually dropping on the rock and is changing the physiognomy of the rock with time, but also with the algae that is growing on it. So there is a sort of symbiotic relationship between the material aggregate and growth and moisture that is gradually changing the components. One of the key pieces that we worked on, and this was back with Marian Coletti as Marcos and Marian, was when we did the folly, the Algazebo for the London Olympics, was we wanted to integrate nature on 3 different scales into the component. And that is that we had a geometric agenda overall. We wanted people to sit in this folly. We had obviously also an aesthetic one altogether. We had a material and structural one. But as you could see, there was something of a relationship between the piece as a sort of exfoliating bark, as a scaffold for bigger growth to happen, down to the control of some carbonated scaffolds in growth medium where algae was growing in a very controlled way around these inner 3D printed scaffolds. So the algae was not simply flowing randomly in the containers, it was actually growing where the carbonation scaffold or the carbonated scaffold was allowing the algae to grow. And it's this sort of condition, simultaneous condition of inserting within a structure growth, but also have the growth on the structure itself from the outside, where we have a reversibility that we find really interesting. Again, small scale, medium scale, large scale, or micro, meso, and macro scale, which we have investigated in these bioreceptive facade panels. This was a funded project of 18 months and is still ongoing, where we looked at different geometries. And we came back to the principle of the bark. And beyond what engineers believe, that it is very much a material phenomenon, we were obsessed with the idea that the geometry of the surface does matter. it has to matter, obviously, because it guides the runoff of the water. It creates shading. It creates different microclimatic ecological systems on a surface according to the different geometries. But beyond that, on these panels, we realize that the distribution of water within the panels also has to do with the amount of evaporation that can happen due to the different geometries that happen. So we started creating a taxonomy of facade panels, from horizontally striated systems to vertically striated ones, to pocket or pochette systems that distributed homogeneously according to a surface, or pinched points where there is a high evaporation on certain areas and in others. This is continuously sort of being explored for different projects, where, as you can see, the pattern complexity is increasing in order to integrate possibly what can be growth in these small crevices. This is for a project of a wall, a bioreceptive wall on a disused platform in East Putney in London, which we are working on with Transport for London. The idea here is that without any irrigation, artificial irrigation or maintenance, we are working on acoustically capable panels, but also bioreceptive panels, where the cryptogams absorb heavy metals from the air and contribute to the fixation of nitrogen and carbon without any additional energy waste or consumption, because the panels and the material itself just does the job. But as you can see, we are interested in how they look like and what these design bark systems can be. Now, these self-generative simulations we do to get there are of the essence. This is not only due to the complexity of the geometry, but it's really to start calibrating the porosity systems through these branched simulations. So what is, in fact, the distance that we have in the porosity that we are creating? How three-dimensional can these branched conditions be? How are they starting to form areas of protuberance and areas where there is an inner condition that has more of a shade or moisture retention capacity? Oops, I missed that one. This seems not to work, because it's another simulation for the outside. It seems not to work. Now, sometimes what happens is that you start simulating what you want to grow, but you start creating such complex models that becomes the leader of what your design is. It starts opening up other questions, other possibilities, whether the internal and external network of these fibrous, porous systems with its own irrigation system internally, externally, creates a completely new setting, completely new horizon. It means that the design of these conditions is then also fabricated in a completely different way, where from the drawing you move onto the robotically printed mechanisms, where three-dimensionality is then created through the layering and intertwining and integration of the growth in these scaffolds. But then there are lots of side effects. There are lots of things that go wrong. And in this case, what happened with the robotic printing of these scaffolds is that due to the lack of control of how they could be printed, there was a curling effect. And the curling effect starts becoming, in fact, the driving motif of the project, because the curling creates a mesoscale of complexity and porosity that helped, for this case, back into the mycelium, a much better matrix for the mycelium to grow into and occupy the screens rather than a linear system. And here you can see some of these exquisitely sort of robotically crafted intricate geometries. A topic that is increasingly important is to deal with viscous matter. And Schneel, who is sitting here with her pieces, but some other work that has been done, is really looking how we can, with moisture presence, print by having a calibration of the material, but also insert and print the growth medium and the species into it simultaneously. This looks easy, but it's extremely complex because there is a desiccation factor obviously implied. Many of the algae species that we have used here can actually not be printed because they might be under such pressure that they stop growing. There's an issue of how much growth medium we insert in some of these components and how the long-term maintenance of them can, in fact, be created. And the two pieces that we have in the exhibition, I think, are currently pretty much sort of the forefront of what I interpret as biointegrated design. This piece here is based on a Caste system with magnesium phosphate concrete. So concrete that is made and composed out of magnesium oxide and phosphates, has a low pH level for the cryptogams, in this case algae, to grow. It has a high level of porosity for water retention, but it also can be cast into these very complex geometries in which the containment of water and growth can be shaded. So a lot of the time was spent on rather exquisite and complex casting systems with multimateriality and overhangs that are very difficult to, in fact, manipulate and control with the molds, with the rubber molds. But all this is only a container for the biophotovoltaics that we were inserting. And here we had Paolo Bombelli from Cambridge, who's pretty much one of the leading experts on biophotovoltaics, giving guidance on how the anode and cathode system had to be integrated into the material. We then did lots of studies with reaction diffusion patterns to look at how we could extend the area of what we call the crown of these components so that the water runoff is not immediate, it's actually slowed down. Because the slower the water runs slightly down into the material, not only through the absorption of the material, but actually through the crevices on the top, the more we have a possibility that the algae keeps moisturized for a longer period of time. And at the same time, the top crown creates a shading system for the underneath receptacles where more water is then in a non-porous environment contained. We did quite a few environmental studies as well to see where the higher insulation rate is happening and how to moisturize. And then the other part is from the experience with hydrogel printing and the laying out of the carbon fibers for the biophotovoltaics, there's for the first time a joint venture between biochemical engineering at UCL, the life sciences at Cambridge, and the Bartlett us as designers, where we're integrating the Caste with the material, the technology of printing robotically with hydrogels that are then calibrated for the algae to grow on it. So there's a very complex integration of species scaffolds from viscous to hard materials into something that can be then exposed to the outside. We're in the process of building these ones here for the London Zoo in London. And the piece that is lying next to it is mainly focused on hydrogels, has a name to create something that is for bioremediation purposes. And this is a research going on, again, in biochemical engineering, where new mechanisms, new species are being studied for bioremediation. But the question is how we architects are starting to design the complexities of the surface with this viscous substratum in which water is slowed down and the bioremediation is heightened, and probably also brought into a scale that is architectural. In other words, these panels are prototypes for something that could happen in the future, which is that we start integrating these designs for bioremediation in our households or in architectural contexts. Again, But lower the music, please. So here we have a sort of the mix of different composites that are then creating that type of hydrogel and tap medium. There's a basic layer of hydrogel, and by the way, the different types of hydrogel consistencies means also that some have more viscosity than others, that some will desiccate whereas others not. So the moisturizing effect of some layers will embed more the algae growth than the other ones, which are just working as an underlying base. And for us architects to work with such sort of flexible, malleable, viscous material is again very difficult to control, very difficult to keep in place, especially for a longer period of time. So I leave with this film of the second piece that we are exhibiting, just to summarize a few points of our research that for me is really important. So on the one hand, we're really using new tools, and the tools are embracing different scales simultaneously. But we're also looking really at this, what I call a paramateriality, beyond the traditional materiality, something of composites where the mixture of materials and the fine-tuning is allowing nature to be integrated in an unprecedented way. We're obviously working in very interdisciplinary ways, we all do that, but I think at some point we're working towards creating a new designer generation. People who have something of a know-how that exists between these disciplines. I'm not sure exactly what that is, but clearly in our program, this is part of the discussion of how much basic knowledge do you need to give people who are able to talk to all these different specialist fields, but still have a sort of overview to control and design with these different factors. We have the scale issues I mentioned, and it goes from the porosity of the material to the very large scale. In our biota lab, clearly not into the scale that Ecologic Studio deals with, and it always fascinates me of, that jump. We are keeping it more in the boundary of the architectural, but between the meso, micro, and macro, we have really grand shifts that are important to look at. And then there is this idea of the scaffold, the bioscaffold, the idea that what we are designing as architects without knowing are in fact substrata or bioscaffolds for growth, for this biocolonization that is happening all the time, and we have wasted huge amounts of resources with in the past to get rid of. And that's why biointegrated design for me means that we are probably looking at designing buildings that are aging. So I'm less interested currently in buildings that are looking fresh and new in the first 3 years. I'm actually much more fascinated what means that the building, how the buildings are operating between the first or after the first 3 years and the next 100 years or 200 years means where the building is not decaying but is aging. Designing for aging buildings and aging architecture is far more interesting in my opinion, because that's what the concept of the architectural bark implies. I'll leave you with that, and maybe we have a bit more of a conversation after that. Thank you very much.